I want to show you a brief intro to this parametrized surface applet that we were gonna work on in class, but didn't have time. So this is where you get, if you click from the Moodle page and then you click on this to get the applet going, it brings up three different windows: the actual surface that you're trying to plot, the domain, which I'll explain in a minute, and then the controls. And so here's a good example to start with. This is parametrizing a sphere, or part of a sphere. And so a parametrized curve just means, put the lines in. Parametrized curve means, or parametrized surface rather, is just the two-dimensional analog of a parametrized curve. We want to create a surface in a way that's very explicit. We don't just want an implicit description like x squared plus y squared plus z squared equals 1. That's great for testing a random point to see if it's on the curve, on the surface. But we want to create the points. And so what we're going to do is we're going to give every point a pair of numbers as its address. And for each address, we're going to create a point using formulas. So we're going to have two variables, two parameters, s and t. And we're going to say have x, y, and z be functions of those guys. So here, and the nice thing here is we've actually already done this. When we did spherical coordinates, we did it even a little bit more than this, which is to have r, theta, and phi. Well, here the theta and phi have just been renamed as s and t, basically. And we've just set the radius to be 1. So instead of describing all of three-dimensional space, we're just describing a surface. So let's see what happens when we vary these things. If I change s, you can see on the domain, all we're doing is we're just saying, okay, s is this fixed value for this red line, and t can be anything. So the s is the analog of the polar, it's the polar angle phi here. And as s gets smaller, you get towards the pole, and s gets bigger, you get away from the pole. And if you fix s and vary t along the red curve, you're varying that theta, you're varying the azimuthal angle, the north, south, east, west angle. And you can see the formulas here. Z is exactly just cosine of s, and so that only depends on s. That's why the red curve is horizontal. It doesn't change in the z. If we look at it sideways, it's horizontal. Whereas the x and y, you take sine of s, which is going to be the radius of this red curve, and then you multiply by cosine t sine t. That gives you a circle. Now what about the blue curve? That's what happens if you fix t and you vary s, and that gives us longitude lines, basically, where we are fixing the azimuthal angle t and changing s, the polar angle. So we can always create in principle, can create surfaces like this by taking any three formulas. X is some whatever function of s and t, y is a function of s and t, z is a function of s and t. And we're going to get a very explicit way of describing a surface. So let's just look at one more example. Let's go back to an even simpler example. What if x was 3 times s plus 2 times t, and y was 2 times s minus 4 times t, and z was 5 times s plus 10 times t. What does that look like? Oh, it's a plane. The scale is not so good. It doesn't seem to be scaling very well. Here, let's see. Let's see if I can get the scale back. No. Okay, so what we can do is we do view, zoom out. Zoom out again. We can also do tools, zoom, and then clicking and dragging actually zooms the thing. I was hoping that this would be nicer. Let's kill the coefficients here a little bit. S minus t. And let's say like 2 times s plus 3 times t. Maybe the numbers were just too big. Okay. Oh yeah, I forgot. You have to press enter in all of the fields. Oh yeah, I was going to mention that. When you're changing these guys, you have to press enter in every single field to get it to be active, and that's probably one thing that's going on here. So, there we go. Okay, it's a little hard to see. Hopefully, yeah, there we go. It's just the shading was kind of weird. So now it's a flat plane, And as I change S and T, I just get these lines. And we've done this before. A long time ago, we talked about how you can parameterize a plane by just taking two vectors and looking at all linear combinations of those vectors. In this case, the vectors would be 1, 1, 2, and 1, minus 1, 3. And we're just taking S times 1, 1, 2 plus T times 1, minus 1, 3. And those vectors are, I hope this comes out in the video here, those vectors, let me drag it over a little bit, are in the directions of the blue and red lines, and then as I change T and S, I just get different mixtures of the two vectors. So that's just a brief introduction, and then you're going to have some problems to think about, at least one problem to think about, entering in different formulas and seeing what you could discover about the shape that you get.